In this final problem, we have a rectangular box with volume 1 cubic foot, and it's to be made with a square base and no top. We want to find the dimensions which require the smallest amount of material. So numerically, we have that volume is 1 cubic foot. We know that we're working with a rectangular box and that it has a square base and no top. We want to find the dimensions which require the smallest amount of material. So let's first draw a picture. So first we should probably get in our box. And so we've made it so it has a square base. So the dimensions on the base would be x width, and x is our length. And then we have a height to it. And we're told, here's our constraint, so our constraint is that the volume is 1. And volume would be x times y, or x squared y. So there's our constraint. We also have, since this has to have volume, that x is positive and y is positive. Can't have negative dimensions for our box. So those are the constraints that I can see so far. Then we have that we want to find the dimensions which require the smallest amount of material. So probably the easiest way to see how the material is built, it's a little bit harder maybe to see in the 3 dimensions, but if we were to slice the box down the sides and open it up, we'd have a shape that looks like this. And we're labeling our variables. So if we slice it open, this is the height of the box. So this would be y, this would be x, y, y, x, y, y, x, y, y, x, and y. And so we can divide this into several sub-rectangles and see that the area of this rectangle is xy, the area of this rectangle is xy, area of this rectangle is xy, xy again. For that rectangle, then the base would have an area of x squared. So we're trying to minimize surface area. That's what's addressed in the problem. And so we have the surface area, let's call it A of xy, would be, well, we've got 4 of these side panels. So it'll be 4xy plus the area of the base. Okay, so that's the function we're trying to minimize. But again, it's got 2 variables, so we need to use our constraint to reduce that down. While over here, we have that from our constraint that xy squared is 1. So this tells us that y is equal to 1 over x squared. So plugging that in for y here, we find that the function that we really want to minimize in terms of one variable is we want to minimize a of x, which is equal to big A of x with y being replaced with x to the minus 2, right? 1 over x squared. And so this would be equal to 4x times x to the minus 2 plus x squared. but that's simply because I've got x and x to the negative 2, so this is 4 times x to the minus 1 plus x squared. And so since we have no boundary points, because x is strictly positive and y is also, we have no boundary conditions. So our only critical values will occur only when the derivative is 0 or doesn't exist. So a prime is equal to negative 4 x to the minus 2 plus 2x. And this doesn't exist when x is 0, but that's outside of our domain. Right? We have that x is strictly positive. So that is not a critical value. Our critical values have to be inside of our domain, and 0 is not in our domain. So the only place where we have a critical value would be when this is equal to 0, which tells me that 2x has got to be equal to 4 x to the minus 2, or dividing by 2 and bringing that over, I get that x cubed is equal to 2, which tells me that x has to be the cube root of 2. That's our only critical value, so we'll put this in here. Our critical value is simply equal to the cube root of 2. That's our only critical value. So now we can use the second derivative test to find out if that really is the min. And so a double prime of x, well, this is what a prime is. So a double prime would be the negative 2 comes down, giving me an 8 x to the minus 3 plus 2. And so a double prime of the cube root of 2, well, I'm going to take the cube root of 2 and cube it. So this would be 8 over the cube root of 2 cubed plus 2. Well, that's just 4 plus 2, which is 6, so that's positive. Since it's a positive, so a of the cube root of 2 is, since this is positive, it's a min. And that's what we were looking for. We wanted to minimize our area. What does the question ask? We want to find the dimensions, so we need to know what y is as well. So here's our formula for y. Y is equal to 1 over x squared. So putting that back in here, if x is the cube root of 2, then y is equal to, again, what is it? 1 over x squared. So it's going to be 1 over the cube root of 2 squared, which is 1 over the cube root of 4. And that's our y value. And so then we can say our final answer is, to minimize material, the base of the box should have length cube root of 2, and the height should be 1 over the cube root of 4 feet. So I hope that these examples give you some sense of how to approach these problems. Again, the common theme is determine what it is you're trying to maximize or minimize. So that's the first formula you should be looking for. And then on top of that, you need to determine what are your constraints. Sometimes those constraints will simply be on the values of x or y, your variables, or other times it will include as well a relationship between your variables x and y. So happy mathing and best of luck.